All right. Hello, everyone. Today we're going to look at this paper, Challenging Common Assumptions in the Unsupervised Learning of Disentangled Representations by Francesco Locatello and a bunch of other people at Google AI, ETH Zurich, and MPI. Full disclaimer, I know these people and I've talked to them about this work, so just so you know where I'm coming from. It's a good paper and it's fairly short to explain. So let's go over it. The main thing here is what's called disentanglement. So disentanglement is kind of a property of data in unsupervised learning, or not data, of your model that you would like to have in unsupervised learning, in here especially in generative models. So what they focus on is like auto-encoding here. And what that means is I have some data point, which could be an image. Let's draw an image here. And I compress this usually into a vector. And the vector has a couple of dimensions. This is a representation of the data. And from this representation, what I can do is I can produce an image again. And if I train an autoencoder, I will enforce that my model, so both of these are my model. This is called an encoder, and this is called a decoder. That what they do is that the final image then looks like the original image. This is an autoencoder, basically a compression algorithm that tries to find representations such that it can reconstruct the original image again. Here we go a little further in that we use what's called variational autoencoders. So all of these experiments here use variants of the variational autoencoder. And what a variational autoencoder, let's skip some here. A variational autoencoder is the same thing as an autoencoder, except it's a probabilistic framework. So what you do is here on the bottom you can see an equation that basically is the objective for a VAE. And what it does is it says, okay, I have an image. Let's say this is my image. And I use an encoder, like in an autoencoder. And that gives me a representation. Okay. But now I don't use this representation directly to decode, but this representation is simply the parameters from a bunch of distributions, right? So here, let's say I have I want four latent factors, and the latent factors are basically the latent variables that describe this image. So the images could be images of, let's say, cats, and four latent factors could be the color of the fur of the cat, the size of the cat, the position in the image, and the, let's say, the general lighting of how bright the image is. So these could be four latent factors that would explain best the image, and from that the image could be best reconstructed, let's say. So the four latent factors we consider as probability distributions. So what our encoder needs to do, our encoder needs to produce 8 numbers in this case. 8 numbers, why? Because for each of these 4 distributions we want a mean and a standard deviation. So these 8 numbers here, each one, or each pair of numbers, one of them is going to be the mean and the other one is going to be the standard deviation of a distribution. And then from these, we're going to construct a distribution. Like so, like, okay, here's the mean, here's the standard deviation, So the distribution somehow looks like this. And then we're going to sample from this distribution. So one sample could be here, one sample could be here, one sample could be here, here. So of course in the middle here we're going to have more samples. But so whereas the autoencoder directly uses the encoding to reproduce the image, the variational autoencoder, what the encoder produces here is simply a parameterization for a distribution, and that distribution then is sampled. So we're going to take one sample here. So from each of these. So there's going to be multiple of those distributions because we have 8 numbers. We are going to produce 4 distributions in particular. So we're going to sample 4 different numbers. So we're going to sample a new vector with 4. 1, 2, 3, 4. Well, I didn't have 8 at the beginning, but never mind. So here, this gives us 4 numbers, but these are sampled. So these are going to be different every time, even if we feed the same image. And from this, the decoder is going to try to reproduce the image. And then, again, the images, the end image and the beginning image are going to be forced to be close to each other. But also now, since this is a probabilistic framework, we also kind of need a different loss function. For the autoencoder, you can simply penalize how far the images are in, let's say, L2 norm. But here, we have 2 distinct parts to the loss term. So, and everything is probabilistic. So let's walk through this here. The first part of so we have 2 parts of the loss term. And here, in particular, Q is, you can see here, it takes as the distribution of Z conditional on X, and Z will always be our latent representation of the data, and X will be the data itself, the data point. So Q will take the data point and produce a Z. And the Z specifically here, what's meant is this thing here. This is Z. Whereas this is X, and this is also, well, this is X tilde or something, whatever is produced by the decoder. So basically, what we're gonna do is we're going to punish the KL distance, which is a probabilistic distance measure. We're going to measure the distance between the distribution of Z under X with the prior over Z. So P of Z here, this here, is the prior distribution over Z. And the prior distribution in VAEs is often to be taken as a Gaussian. So we'll say, all right, so our kind of default assumption on the Z variables is that they're Gaussians here. And we're gonna force, basically, we're gonna force the encoder to come up with encodings generally over the data set that are Gaussians, that are conformal to our prior. So here we say specific prior PZ. Oh, I didn't mean to cross that out. Right. So this second term enforces the encoder to produce things that are Gaussian. Specifically, if our prior is, let's say, zero mean unit variance Gaussians, it's going to enforce that. The first term here is different. The first term makes the image that has been input to the variational autoencoder and the image that has been output close together. Again, this is a probabilistic loss, so what we're going to do here is we're going to take expectations. So the KL distance is also an expectation, by the way. We're going to take expectations over px, which is the distribution of the data, and also over q. And q is, again, our encoding mechanism. And we're simply going to punish or we're going to here maximize the log probability, which is equivalent to minimizing the negative log likelihood, which you might be familiar with, of the data given the z variables. So, and this is an expectation over q given x. So what that means is basically we want the probability of this original data point. We want, here we output x tilde. We want this to be close to x here. So what we can say is we want the probability that our model outputs x, which has been the original input, right, given this particular z that it produced, to be high, as an expectation of q of z given x. So it's a bit cryptic, but it means here I input x into q, I get out z, and when I have the z, what I produce, here is what I produce, the likelihood that x, the original image, see, these are the same, is produced should be high. So that's a variational autoencoder. I simply encourage the latent representations to be close to my prior, which is often Gaussian, and I encourage the output to be similar to the input, which I do by encouraging the likelihood that the output is the input. All right, so cool. So what does that have to do with disentanglement? Disentanglement is a property that now I would like to have in my model, which is that these things here, or we can also focus on these things here, however you want to view it, or these things here, these latent things that my encoder outputs somehow give me information about the data in a way that's disentangled. What that means is I've made an example that's already disentangled, where I said let's say we have images of cats, and the fur color is going to be one variable, and the color of the eyes of the cat is going to be another one, and the position in the image is going to be another one. So these are all fairly independent, right? And so if I change some latent factor, I can change them pretty much independently. So here, this could be the fur color. I can change it pretty much independently, and the cat will just have a different fur and so on. What would be non-disentangled representations would be, let's say one encodes the fur of the cat, and the other one encodes the species of cat, because these are highly, let's say, entangled. So the fur color is highly dependent on what species the cat is, and it's not really, so they kind of, you can imagine it as these things being correlated, but it's slightly different. And there's not an agreement on what disentanglement means, really. We just kind of imagine data is somehow entangled, and we want to kind of pull out these disentangled factors. So what they focus on here, and the easiest measure here, is the following. I might want to have some space. All right, so the easiest measure of disentanglement that is come up with here is the following. It's an assumption. The assumption is, let's say there's data, x, right? We'll call it a random variable. And we assume that this data is generated by a bunch of latent variables, z1, z2, z3, which are independent, which means that, and the technical thing for this is that the p of z, which is all of them, can be factorized into p of zi. So they are independent. And these kind of determine independently the data x. Now, what does that disentanglement of when my model has produced a disentangled representation means? I now have a model, some model, M, which is going to give me a representation of x. And the representation, as we saw before, could be these things here. That's that representation. Specifically, what these people do is they say, okay, the mean of the distribution that my encoder gives me, that's the representation of x. All right, so this gives you a representation of x from which you then might want to, reconstruct x over here, x to them. But so the important thing is, when is the representation disentangled? The representation is disentangled in the easiest sense if the following holds. When I change zi, so I introduce a delta to zi to any of these three, that means that in the representation of x, which we're just going to say, so if there's 3 dimensions of z, we just assume kind of we know that, and we also make the representation 3-dimensional, then exactly one factor in this is going to change. So if I change one factor of the true underlying distribution, which is independently, which all the latent factors are independent, then only one factor in my representation changes. So if that's the case, then kind of I can be fairly sure that I've captured the true latent structure of the data, right? If I change one of the z here, let's say I change z3, and only then r3. So I change z3. Let's say I have access to the true underlying distribution. I ask the world to give me a picture of a cat where the fur color is different, and then I put it. I get a data point, and then I put it through my model. I get a representation, and only from the cat that I had before, only one of the factors of my representation changes. Then I call it disentangled. Then I can be fairly sure, okay, my representation, this dimension of my representation captures the fur color independently of the other factors. All right, so that's disentanglement. And you notice it requires actually access here to the true distribution of how the data is generated by the world. So this is something you generally don't have, but it's a technical notion. So you can certainly postulate it, and it's a nice framework. And this paper basically proves that generally learning disentangled representation in that way is impossible. If you don't make some assumptions, some a priori assumptions on your data and your model. So this is a theorem here, and we see here P is any generative model which admits this factorization, right? That's what we talked about. The true underlying generative process is independent in its constituents. That means there's a bunch of latent variables. They independently from each other produce a data point, right? X is the data observations. then there exists an infinite family of bijective functions, right, such that this and this and this and this. Okay, what that means is, so this thing here basically just means that the distributions agree. So the overall distributions, let's say it's not exactly that, but the posterior distributions, let's say the data looks the same, right? That what comes out of the process looks the same. So there is functions that transform the latent distribution into some other distribution, but they look the same in cumulatively. All right, and then this part here means you'll see the derivative of fi of u with respect to some uj, which you'll notice I and j are different. This means that basically the dimensions are entangled. It means that if I take the derivative of one entry in the function output and I derive it by another entry, then I get a non-zero derivative, which means that this uj influences fi, which basically means that I can take the z, I can transform it in, so z is independent, so it means the ith dimension has no influence on the jth dimension of the output, and I can transform it into something where that's no longer the case, where the ith and the jth dimension very much kind of are entangled or covariate. So this means I can take the z that's kind of everything is independent, and I can transform it into something where everything is dependent. And they give a nice example here. So they say, let's say we have Gaussians in 2 dimensions. So we have one Gaussian here, and let me see if I can draw this, one Gaussian here, right, in 2 dimensions. They're completely independent. What you'll find is that the kind of distribution overall has iso lines like this, right? It gives you kind of a hump in the middle, 2-dimensionally. You can maybe imagine like a bit of a mountain in the middle. All right, so this is the kind of output distribution. If you don't know about the underlying factors, you simply see the cumulative distribution, which would be the big P here. All right, now we transform this with f, and f is simply a rotation by 45 degrees. Right, so 2 new axes, this and that, and again, our 2 Gaussians are going to be transformed of these, right? So these are not disentangled anymore. Well, in the notion, I can't say it like this, but this is easiest to say. So these are kind of, now that it's rotated in terms of the original coordinate system, which would go like this, these very much depend on each other, right? The jth dimension and the ith dimension depend on each other, because if I sample from one of the Gaussians, I need now basically 2 coordinates to describe where it is. Or, yeah, one isn't just... so if I sample from one Gaussian, I need both the coordinates. But the cumulative distribution, or is still going to look exactly the same. So it's again a hump. So it's basically an isometric hump in every direction. If I rotate that, it looks exactly the same. This is the P here. Right? But now the ith dimension and the jth dimension very much influence each other. And yeah, interestingly, if you now look at disentanglement, if I now produce data x here, x1, and here I produce data x2, and both go through my model and give me our representation of x1 and the representation of x2, I have, without seeing the underlying structure, I have no idea which one of those two it comes from, and thereby I have zero chance. Basically, it's a lucky guess which one it comes from, and there's an infinite family, so I will never find the true underlying distribution here, and thereby I will never be able to satisfy this property that if one of the z changes, then only one of the factors of my representation will change. Because if I say, oh, well, obviously this is the case, then I'm going to make a different model. And if I say, well, this is the case, I'm going to make a different model. I don't know which one it is, so I have to choose one. And it could be the other one, so I'm bound to be wrong, in this case 50% of the time. But if it's an infinite family, I'm bound to be wrong every time, basically. So that's what the theorem basically says. I can't decide on the true underlying distribution. There's an infinite family that transforms it transforms every distribution into some other distribution that has basically complete opposite properties of entanglement, and I need to choose one, and I will never choose the right one because I'm not that lucky, and thereby I can't do representation learning that's disentangled. All right, so that's the main claim of the paper, and there is a lot of experiments here. So what the paper also does is they produce some new data sets and they test a lot of architectures. Basically, they say just because it's theoretically impossible, it's not impractical, because we can actually make these underlying assumptions. Like, we can make some assumptions on the data, and then we kind of can attempt to do disentanglement learning. So they do these data sets and they test different VAEs, architectures on it, and they basically establish where more work should go. So that's kind of the rest of the paper. I encourage you to look at the rest of the paper. I just wanted to give a quick introduction to VAEs and to disentanglement, disentangled representation learning. I wasn't technically correct in every detail, but I hope that it's enough, and have fun.